Well, the design productivity gap is one point that has been the cross product or the product of Moore's law. And Moore's law stated that transistor capacity has doubled every 18 months, right? So this law used to hold quite true for the ICs, but currently this law is not rightly applicable. There are modifications to this law. Anyways, the impact of this law and this scenario is very important. So what is basically the design productivity gap? While designer productivity has grown at an impressive rate, right, but the rate of improvement has not kept pace with chip capacity. Well, chip capacity has been the product of integration, right, and the level of integration have increased a lot. So this is basically the IC capacity or the level of integration going like this. And what is productivity? Productivity is the number of transistors or the complexity of the design that can be created. It means that IC capacity is the capability to integrate more chips has increased at a very great rate, and but the designer productivity has not kept pace with this particular trend. Now what does this figure means? That basically there are two axes. This axis tells us about the IC capacity or the integration, while this capacity, this scale gives us the productivity or the capacity of the designers to design complex circuits. So for example, if we look at 1981, right, and when we look at 1981, the IC capacity per chip was at 0.01 million, right, and 0.01 million equals 10,000. And looking at this scale, basically in 1981, what was it? It was about 0.1 into k or 1000 or 100. Now the integration level is basically 0.01 into 1 million, which is 10,000, and designer productivity is basically 0.1 into 1000, which is 100. So if we can do something like this, right, we can do a calculation. We can divide this term by this term. So we can have 10,000 transistors divided by 100 transistors per staff month. Okay, so if we can divide that, this transistors cancel, and we get what? 100 staff months. Now when we give 100 staff months or 100 design months, we can have this type of calculations like we followed before. Now we can do the same thing for 2002, which basically we can do the calculations, right? I would like all to please refer to this diagram and do the calculations. So we can have a calculation for 1981 like we discussed before. Similarly, we can do the calculation for 2002. We can draw a line from here, and this line is touching at this point. So this is the point slightly above 100, so it can be taken as 150, and this point on this axis is between 1 and 10, which is 5. So what is the IC capacity? Is 150 million or 150,000. And what is basically the productivity? It is 5 into 1000 or 5000. So dividing, we get in 2002 to design a leading chip we need 30,000 designer months. Now we can also calculate the cost of production, right? If one designer month costs $10,000, we can do the calculations for 1981 and 2002. Please do the calculations. Now when we do the calculations, we come in 1981, the cost comes out to be $1 million, while the cost in 2002 comes out to be $300 million. See the dramatic increase in the cost. So this cost is increasing because this gap is increasing. So several approaches have been taken to decrease this gap of design productivity. One of the approaches have been to have a team of designers. One designer can design less transistors, but a team of designers can produce more transistors. So one of the things have been to have a team of designers. Now after having the team of designers, we can have some calculations like this. This is the concept called mythical man month. So we have a designer team that is designing an IC now. So in theory, adding designers to team reduces project completion time or increases productivity, right? One designer can produce less number of transistors and more designers can produce more number of transistors. But in reality, productivity per designer decreases due to the complexities of team management and communication. So in order to communicate with the designers, you need a large team. And when you're communicating with a large team, there can be difficulties like not proper communication that can result in more problems rather than benefits. So in software community, we call this as the mythical man month, and at some point this effect can be so bad it can even lengthen the project completion time. So we have this figure, right, and we have, let's say, and this is the number of designers, right? One of the designers, this is the number of designers, and this is the project completion time. So the scenario is able to communicate that we have a project of 1 billion transistors that we have to make, and one designer can design 5,000 transistors per month, right? So it is further given that each individual designer that we add to the team reduces the number of transistors by 100 transistors per month. What does this mean? This means two designers produce 4,900 transistors per month each, and so on and so forth. So in order to do that thing, we need an equation, right? So I would invite you to try to write an equation for the team productivity, right? So the total number of transistors that can be made by an individual, right? So what is that equation? It would be 5,100 plus 100n, right? When n is 1, we have one designer, right? The number of transistors produces 5,100 minus 100 or 5,000. When we have two designers, the number of transistors would be 4,900 and so on. So this satisfies that, right? So this is the individual productivity, right? And this individual productivity is given by this particular line, straight line. It starts with zero number of designers as 5,000 and it goes down as the number of designers are increased, right? So now I would invite you to use this concept to find the expression for team productivity. So team productivity would be given as this expression multiplied by the value of n or total designers, right? So what we can write, how we can write? We can write as team productivity as 5,100 minus 100 n whole, this is the individual productivity, right, multiplied by the number of designers. So this would be the expression for team productivity. Now use this expression. Now can you verify this? This would be an n square term, right? So how we can see it on the graph? It is a parabola. it's a parabolic curve. Okay, so this is what we can do. Now what we can do is we can find the value of n for maximum team productivity, right? So any clues for finding the value of n for maximum team productivity? You differentiate this expression with respect to n and then equate to 0 for the maximum point. Now please do that and give me an expression for the value, for the maximum value of number of designers. So this is the individual productivity multiplied by the number of members, which is team productivity. We expand this, we differentiate with respect to n to get this value, and then we equate it to 0 to find the maximum point. Maximum point comes out to be n equals 25.5, which means at 25.5 and 25 and 26 point, which is this or this, we have the maximum team productivity. Productivity increases up to the number of 25 designers and 26 designers. Then when we increase the number of designers, the team productivity starts to decrease instead of increasing. So that is the whole point of this full calculation. Now you can find the time to completion for this particular point, which is n equals 25 or and n equals 26. So summarizing, embedded systems are everywhere. What is the key challenge? Optimization of design metrics, because design metrics compete with one another. Making one better would make the other worse, and so on. A unified view of hardware and software is necessary to improve productivity, because you have to do co-design and you have to do project partitioning into hardware and software. Unless you are an expert of both hardware and software, you cannot do that. So we have three key technologies: processor technologies, which can be selected. Then we can select the IC technology for a particular project. Then we can select the design technology for a particular project. This winds up our discussion.